Okay. You like that? Oh, okay. Subtraction, of course, tells us what? What does subtraction tell us for numbers?
Shortcut minus.
How? What's 10 minus 7? 3, because 7 and 10 are 3 apart. So it talks about distance, of course, right? And you take an absolute value of 1 and come up on it, all that kind of bullshit, right? So u minus v will somehow visually be representative of how far apart the vectors are. Right? So where's this vector end up here? Where's this vector end up here? So where should u minus v be? It should be sort of somehow here. I don't know if you guys... Let me see if that makes any kind of sense. So there's a few ways I can explain this. That's one way I can explain subtraction. And in fact, how did I want to say this? Yeah, we could do that. It's the result is always going to point in the direction of the positive one. So if I had u minus v, this would be the answer to u minus v. That's u minus v. Let's really analyze a different way why that would have to be true. So let me just give myself some stuff. Let's say that this is a vector A. And please notice the book has the advantage of being able to write things in bold. I can't really do that very easily. So I'm going to use these little vector symbols. The book sometimes uses it, but mostly they put vectors in bold. So if you see a letter in bold, that's a vector. If you see a letter, normally it's in cursive or italics and not bolded, that's going to be a scalar, a number. Is that cool? Okay. And I have this other vector, let's say b. So I want to see what a minus b is. Now you might be able to tell what I'm trying to do here. So if I subtract b from a, I'm actually going to end up having the result should be here. I'm going to subtract that part off of a. So a minus b should end up being sort of straight across if this was a little bit shorter. You guys see what I'm trying to do there? Another way you can do this is the answer to a minus b has to be the vector. Let me see if I can say this correctly. So let me put these together. Stay with me now. All right, this is neat. I don't know if that made sense to somebody. There's a lot of different ways to look at this. If I took that away from this, it should just flatten it. Because I'm basically taking away the y piece. Now, if I rotate these, that idea still remains. It's just easier if I make one of them purely in one direction to talk about it. All right, now if you don't like that, here's something else. The answer to a minus b has to be the thing where if I do b plus a minus b, the answer should be a, right? So if I, where must the answer be? So that if I add a to it, it's going to end up being, if I add b to it, it's going to end up being a. It's got to be this, right? Same answer. I'm not giving it numbers right now because I just want to get the idea down. So there's another kind of way to think about it, is think about it backwards. Where does it have to be so that it plus b equals a? Well, it must be this one. When I go b, there, now I end up being a. Okay, maybe. So that, again, is not just connecting the endpoints, connecting the endpoints. Right? So if I take, what did I say, u, and I subtract v from it, and v is mostly, let me see how, this is not the best picture to try to work from. If I take u and try to subtract v from it, then it is going to take away all this upward. It's going to end up being down. I mean, v is almost all up. So it kind of makes sense that the result is almost all down. I'm taking all that up away. Yes?
So when you were talking about the a and b right now, were you saying that, okay, if you were to subtract a, or is it b from a?
Yeah, b from a.
If you were to take the connecting vector and put it near the, like, if you were to move it and put it near the origin, it'd be like flat. Is that what you were saying?
Yeah, so this is one way to look at it. Now, the way I was talking about it a minute ago first was, if I take this piece away from this,
yeah,
it'll basically be this, which is actually a third way to think of it.
Okay, yeah.
A minus b is a plus negative b. And what do you think negative b is going to be? It's just going to be this pointing. Yeah, so here's a plus negative b. Again, the same answer. Yes, sir.
Do you mind doing the math like you did with u plus v? Could you show us u minus v, or is there a way to do the math?
Well, I mean, the math, thankfully, is because of the fact that this is the same as this, I can just use the addition property, and when I want to subtract two things, I just have to subtract the components. So let's look. What does it look like this is going to be? If I moved this to the origin, my really rough scale here, if I pick this up and move it here, you guys still with me? So I can investigate what the name of this resultant vector is, right? It really doesn't matter where a vector sits. I can always move it to the origin to see what its name is. Cool? If I just had I want to be a little more precise with this, but my scale sucks anyway, so here's. It's a little bit shorter than that. It's roughly that way, so it looks like maybe right there. Of course, what's the actual answer? Well, what's u minus v going to be? 2, 1 minus 1, 3 is going to be 1, negative 2. 1, negative 2. Look at that, Jay! So, again, some of you guys are like, why the shit didn't you just do that in the first place? Because we have to understand both visually and algebraically, computationally, what's going on. Because there will be problems that ask you to do something purely visually. They won't give you any coordinates. You just have to kind of retrace it, orient them correctly, and give me the resultant answer. Right? Because, I don't know, at this point you guys should realize that certain things are easier to do visually and certain things are easier to do computationally. So thank God, you get further along in math, you can do an entire proofs by translating your problem into a visual representation and then translate it back, because it's easier visually. Or it's easier to use a different coordinate system, which we'll learn more about later. You've already learned polar coordinates, but we're going to learn the 3D extension of that, right? So it might be easier to do a problem in a different coordinate system. I like it. All right, maybe. But this is really sort of on the level of just take this and put this here and then draw between the two, and there's the answer. It's amazing. You know, it's almost like construction paper kind of stuff going on. I mean, it's nothing too intense yet. Again, I'll have to see. Wait until if you try these, what you think. Okay. Oh, I already did that. Oh, okay. Thankfully, I tried not to give you too many problems where it's 3D, because then the visual analog is not as enlightening, because it's kind of hard to tell. If I do everything right and I graph a point exactly where it should be, and then I step back, somebody else could think it's somewhere entirely different, because of perspective problems with a 2D board trying to show me 3D information. So if you graph a vector in 3D and another vector in 3D, and then you graph the subtraction between them, when you step back, it doesn't tell you anything, really. Do you understand what I'm saying? But 2D, you can completely see the idea visually of what you're doing between the two vectors. So I try to assign a lot of 2D where you have to draw the vectors out. I guess you'll find out. Okay.
Can we do a 3D?
Say again?
Can we do a 3D subtraction of vectors?
Yeah, I just wouldn't do it visually, because like I just said, it doesn't really... It would be the same idea. In fact, I want you to realize something. How many dimensions does that live in? Can't say. I drew it with the intention that it lives in 507 dimensions. And I'm right. It lives in how many freaking dimensions I want it to live in. I want you to realize this. When I have a line, it lives in one dimension, fundamentally it lives in one dimension in a sense. But it lives in this room, so it lives in 3 dimensions. This room lives in whatever other dimensions, physical or time or whatever the shit it is, right? Do you understand what I'm saying right now? So, the problem when you have 2 vectors in 3 dimensions, if I draw this vector here, is that vector behind it? Is it in front of it? Is it in the same plane? Can you tell me? You cannot, right? You can say, well, then make it thicker if it's towards me. No, you know, why do that? Make it skinny if it's way far away. Put some glaze over it so I know it's like way far away. You know, I'm being... you have to be able to draw some stuff in 3D, but I want you to see the limitations of learning from doing something in 3D. You have to be able, eventually in this class, you're going to be drawing some shapes in 3D. Given an equation, you can draw the shape. It's going to be everything from beautiful to completely gross. And I can say that because mine are going to be probably grosser, right? It's just the way it is. But hopefully the graph paper I'm going to give you is going to help out a little bit. 3D is not easy to work with because we don't work with it normally, right? We don't have a nice way to represent it. Okay. I'm going to do one more idea, and then I'm going to let you guys attack this little handout that I've got. That's the length of a vector. Now, I can talk about 2D, but I don't care how many D you live in. I mean, hopefully the length of a vector is just immediately obvious what it's going to be. So if this vector is the vector, what you got, Jeff? I don't know, Jeff. A1, B1. That's sure, why not, Jeff? Then how long is that vector? It's not A plus B. It's just made a triangle, right? So it's A squared plus, yeah. So the length of this is how we represent the length of a vector, is those absolute value symbols. So to be honest, the absolute value, we use that terminology for a one-dimensional length. I want you to realize, if I have just one dimension, and I say, well, how long is the vector that points to 4? Well, how long is it? 4. How long is the vector that points to -4? How long is it? 4. So when I say the absolute value -4, I am actually asking you the length of the vector that points to -4. You just wouldn't say that before now, right? But now I can realize that's what we're saying. So that's why the symbol for length of a vector are the absolute value symbols. Because that's really what it means. It's the length of the thing. You guys kind of with me? So this is just going to be the square root A1 squared plus B1 squared. Yeah. Gotta love that shit. Alright, so what's the length of the vector 1, 2, -5? Yeah, square root of 1 plus 4 plus 25, right? Square root of 30. I like it. Yeah. Cool. Let that be nice as hell, right? So the length of a vector is always easy to figure out. I don't care how many dimensions, then you just keep adding some stuff in there, right? 4 dimensions, there'll be one more plus in there. Ooh. Okay, so with all that said, let me give you this. If you really desperately want to work as a lone wolf, you can, but I would love it if you worked together with somebody, or do some and then check it out with somebody near you. You know what I mean? You don't have to be on for this.